Good morning. Thanks for joining me. If you've never been on my channel before, my name is Warren Sims. I'm a student here at Tennessee Tech University in Cookeville, Tennessee. I'm currently doing some research with Dr. Pardue here involving signal processing. Now, if you all have been on my channel before, you'll realize it's been quite a while since I posted a video, and I apologize for that. Stayed pretty busy over Christmas break, and as soon as I came back, just keeping up with classes and trying to keep a leg up on everything. But I have been up to quite a bit research-wise. I hope you all had a wonderful and Merry Christmas and a Happy New Year with all your family and friends. And let's go ahead and get into it. Okay. All right. I apologize for this. I still sometimes have to fight with the Zoom, but that's okay. Well, the first thing that I've been working on is I've been reading into decibels as a unit. This builds quite nicely after my previous project in MATLAB involving using sound files in MATLAB. So it's kind of cool how they've kind of related. The decibel is a logarithmic unit, as many of you all probably already know. And we were looking at originally at our first meeting how to graph the readings of these decibels and what exactly is decibels unit. As I said before, it's a logarithmic based unit where if you're unsure about what a logarithmic value is, it's on a base 10. So each time you're going up by a power of 10 and a power of 10. So if I can scroll back up here, like the difference in sound level. So for example, there's a sound that has 10 times the power of the first, the difference in decibels will be 10 decibels because it's 10 times the power of the original sound, if that makes sense. This is also this is in effect due to the fact of the drastic differences in how sound is perceived, if that makes sense. The standard reference levels, the absolute sound levels, is around 20 micropascals for air. This is very low, 10 billionths of the atmosphere. And as it says right here, it's usually only found in younger people who have not been exposed to loud music, while personal sound systems such as earbuds, loudspeakers can continue to put a dampening on that. This whole article just goes into talking about how not all pressures are equally perceived, goes into fons and sones, and I hope to come back to this at a later date once I get to one of the projects that I've been passing back and forth. I'm going to tell you all about in a little bit. So I thought this would just be a good way to introduce you all to decibels, and this is a really nifty website for teaching you a little bit about them and explaining it way better than I can. Okay, so let's hop on over here. A real treat when I got back, Dr. Pardue introduced me and my research partner Tim to the brand new oscilloscope that the ME department has recently received, just like the one that you see on the screen. Beautiful, high quality, just a wonderful, wonderful machine to play around with and have some fun with. This semester has actually been my first real hands-on experience with an oscilloscope, and I've been having a lot of fun with it. If you do not know what an oscilloscope is, it allows you to hook up a function generator to it and generate various wave functions at various frequencies. You can go through and adjust everything on it and analyze these waves and mathematically analyze them and just get a good idea for what's going on. And this thing has so many bells and whistles, and I've been looking into to some videos and stuff on how to use it and some cool functions that go along with it. And it's very, very fascinating. I really look forward to continue playing around with it and figuring out what all it can really do. Now, moving on a little further, um, I thought it might be a good idea if you all got a look at what an oscilloscope does. So this is your screen on your oscilloscope right here. Your system, as I previously stated, is hooked up to a function generator that generates it, and all this input stuff over here acts as that. So we're saying we want a sine wave with the amplitude of 5 volts, as we have right here. We can adjust our frequency out just as we would. Let's take that up, take that down, excuse me, to 100 hertz. See, it's less frequent. And we can take it up to 1,000 hertz, which is very fast. Your gain, your time, up to that. It opens up your frame on your view to allow for more wave, a greater portion of the wavelength to appear in the screen, which is very cool. We can adjust our voltage, which in turn adjusts our amplitude of our waves, and just a whole lot of really interesting things. It's a great way to analyze electrical signals, get feedback from various sensors and pressures and impacts, and just anything that involves energy data is a great way to imagine it. Now, another really cool thing that Dr. Pardue introduced me and Tim to, I believe it's been 2 weeks ago at this point, was bear with me on this, a piezoelectric accelerometer. Now, that's a mouthful, for sure. But what does an accelerometer act as? It's basically, the easiest way to explain it is like a vibration sensor. The one that we personally took a look at was one that can be threaded onto a machine, like it's got bolt threads on it, and it's mounted onto the machine where it can sense the vibration of it. And me and Tim had a whole lot of fun hooking it up to that brand new oscilloscope and manually holding it down and attaching it to a table. And then on various places, we tap on the table and see the reading on it. And we were also using the freeze frame feature on the oscilloscope, so we could capture that segment in time and then further analyze the data obtained at various moments. So it was really cool. But how this accelerometer works, it has a piece of crystal inside of it, isolated from the base, and that crystal moves, and its movement dictates what your output will be. It's really, really interesting. It's a special type of crystal inside of it. Let me see if I can find a little more. I wonder if I can pull. I'll zoom in for you all. I was hoping it'd have a little bit better of an explanation where it would explain it a little slightly better than I would. But see, it's a little fuzzy, but there's this piezoelectric material right here, and that's that crystal, along with a mass that comes in contact with the crystal, and that's what generates your output, the reading from that. So it's just really cool knowing why the accelerometer works and how it goes about working. So that's another cool thing that I've recently been exposed to and wanted some more on. So why is this vibration important? Well, as an engineer, as a future engineer, it's important to keep in mind the natural frequencies of materials, such as bridges, even though I probably won't be involved as much with this as the civil engineers will. But it's still very important to keep in mind due to the fact that I'll be working on plenty of equipment that has its own personal natural frequencies of vibration that could lead to catastrophic failure if it's ignored. Structure fallacies such as these were that their natural frequency of the structure itself matched the environmental vibration, which led to the catastrophic collapse. So all this has to be paid attention to majorly concerning the use of materials and the safety of the public. Just a very, very interesting thing that I've been introduced to over the past bit. And this actually came up very much in my statics class. So it was cool to see another application of it. Okay, now this is kind of fun. If any of you all have been around and heard about some of the case studies we've been looking at over the past bit, we've been working with the Intro to Signal Processing, a pragmatic introduction to signal processing by Tom O'Haver, and been taking a look at case studies. Well, the one that I've been reading into recently is case study W, miniaturized signal processing the Raspberry Pi. Now, this article is about the Raspberry Pi and similarly Arduino units and things such as that. And I actually, for Christmas, received a little Arduino kit. And I'm really looking forward to playing around with this and getting some of the data over into MATLAB and analyzing it. And it came with all sorts of various little sensors that I'm really looking forward to collecting the data from and having some fun with it. I'm going to keep you all updated, and hopefully later this week, when things calm down a little bit, I can sit down and piece together a little design I've been looking at for my kit and get some measurements and maybe share it with you all. Oh, I apologize. I accidentally zoomed in. Again, trying to swap over to a screen. Bear with me. Okay. We're back to this now. Good deal. Okay. So if I can move this over, that would be great. Okay. So these were some cool little projects that I could use my Arduino. I don't think I'm going to go exactly with this. I'm probably going to work some with the potentiometer that it has, and just gonna see what I can come up with. I think it'll be a whole lot of fun. Now, another little minor thing that I've been thinking about was if anybody who's watching this knows me, they know I absolutely love fishing. I mean, I always have and always will. One thing that I've been taking interest to, and I've never really fooled around with them much. Like me and my dad had one, growing up going fishing, but we never really used it. Are fish finders. Basically, it's a form. It's a. How can I explain this? A replication of echolocation that animals utilize in a sense. It's sonar. That's the best way to put it. The screen that you see here currently is just a mapper, is just a visual screen, a monitor of what the sensor is picking up and showing. It acts very much like the oscilloscope does by giving feedback and graph data of what's actually going on with your sensors and your generators and stuff such like that in the oscilloscope example. But this acts with a little sensor probe that is placed down in the water that sends out signals, and the signals bounce back and dictate foreign objects in the water, things that break the signal and send it back and give a general idea of the size and the depth and everything. It's very much like the echolocation utilized by animals, where sound waves are sent out into the water and then received to show an interference in the signal and give an idea of give the idea of what's in the path. And here comes our good friend the decibel once again. So just another way that it ties in with that again. It's just cool, all the overlap and how all this builds on. Similar to the sonar that the Navy uses. All this has been adapted for the utilization of mankind to try to really get something amazing from the animal kingdom, and how we can really make some very useful and amazing tools from it. And I'm really looking forward into further investigating this, and I've had fun with the little bit that I have had the opportunity to take a look at. Okay, I'm gonna wrap it up probably in the next little bit, and hopefully get a video out to you guys next week. Oh, another thing is, me and Tim at our previous meeting played around a little more with Octave. Now, if you all don't know, Octave is a basically a free version of MATLAB. It doesn't have as many bells and whistles, but it's very useful itself. I'll hop over here real quick and just give you a view. This is Octave, very much just like the layout of MATLAB. It just doesn't have as much capabilities or realistically as many bells and whistles. It's kind of like a neck down version of MATLAB, but it's still extremely useful. And as I said before, it's free, so it's a nice way for people who don't really have the funding to purchase MATLAB or just need to have a really nice tool to help out and solve some problems with and do some basic functions and readouts. It's a very, very useful tool that I suggest giving it a try. Well, I believe that's pretty well the update on my end. And excuse me, let me try to hop back over here. There we go. And I'd like to thank you all for taking a minute and listening to my little spiel. And I'll be back, and I hope you all have a wonderful week and good luck. And I'll catch you all later. Goodbye.